Next, we discuss the Poisson distribution. In this video, we have a short introduction about Poisson distribution, examples, probability mass function of Poisson distribution, and also the approximation of binomial distribution using Poisson distribution. Earlier, we discussed binomial distribution in detail. There, a random variable x represents number of successes in n trials. That means if you have a random experiment in which occurrence of some outcomes were regarded as success and their non-occurrence regarded as failure, and the experiment is repeated n times, and we introduce a random variable x representing number of successes in n trials, then x has values 0, 1 to etc. n, and its probabilities are given by this binomial distribution. That means the equation p of x equal to ncx p raised to x q raised to n minus x offers the probability of this x equal to 0 or x equal to 1, x equal to 2, etc. x equal to n. We note that the number of trials n is fixed in binomial distribution. That is, the variable x can go from values 0, 1, 2, etc. n. But there are many situations where we cannot have a fixed value for n, especially the random variables representing occurrences of number of phone calls received in an office, number of accidents occurring in a district, number of suicides reported in a district on a day, the number of vehicles waiting in a traffic jam, number of customers waiting for service in a counter. In all these cases, we don't have a fixed value for the number of trials n. We can count only the number of occurrences of the event. The number of times the event occurs, that only we can count, but we cannot count the total number of trials in these cases. Suppose x represents the number of counts of these events, then x cannot be binomial because the number of trials is fixed. So in those situations, we can make use of Poisson distribution to address the probability distribution of the variable x. Clearly, x is a discrete random variable because x has values 0, 1, 2, etc. And we say that 0, 1, 2, etc. because the values of the variable x are unlimited. But theoretically, the values are treated as unlimited. Practically, there may be some fixed value or some finite value for the variable x. If you consider the number of vehicles waiting in a traffic jam, there may be the number of vehicles, some 5 or 6, etc. But theoretically speaking, the number of values of the variable cannot be stipulated at some 5 or 6, etc. Now, the Poisson distribution is a discrete probability distribution, and it can be used to address the probability behavior of these variables representing the number of occurrences of an event in a duration of time, region, or space, etc. Now, this is introduced by the French mathematician Simeon Denis Poisson. Now, you see that the variable x is said to follow Poisson distribution if its equation is e raised to minus lambda, lambda raised to x by x factorial, and the values of x are 0, 1, 2, etc. The lambda, the constant of the distribution, is greater than 0, and e is approximately equal to 2.71828, etc. We normally take it up to 4 or 5 digits, and it is also treated as the limit of 1 plus 1 by n whole raised to n when n tends to infinity. We know that when n is 1, it is 2, and n is 2, 1 plus 1 by 2 whole square, and it goes like that. When n becomes larger and larger, this 1 plus 1 by n whole power n becomes closer and closer to 2.718, etc. It is non-terminating and non-recurring value. So we consider approximately up to 4 or 5 digits. Anyway, it is the limit of 1 plus 1 by n whole power n. Can also see that e raised to x is an exponential function and it is 1 plus x by 1 factorial, x square by 2 factorial plus x cube by 3 factorial plus etc. And it can be written as the summing using the summing operator, summation r equals 0 to infinity x power r by r factorial. Now this expansion can be considered as the starting point of introducing this equation p of x equal to e raised to minus lambda, lambda raised to x by x factorial. If we consider this as e raised to lambda, this will be 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus lambda cube by 3 factorial plus etc. Now, to make this as a probability distribution, we should get the two properties of probability distribution. The first property is the positiveness, and second property is the total probability of all the values of the variable is equal to 1. So in this case, if you multiply the left side and right side of this equation with e raised to minus lambda, it becomes e raised to minus lambda the left side into e raised to lambda equals 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus lambda cube by 3 factorial plus etc. Since the left side is e raised to minus lambda into e raised to lambda, it is 1. The right side is 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus lambda cube by 3 factorial plus etc. into e raised to minus lambda. If we open the bracket, it is 1 into e raised to minus lambda, lambda into e raised to minus lambda by 1 factorial, lambda square into e raised to minus lambda by 2 factorial, etc. The same terms we get when we put x 0, 1 to etc. in this equation. When x is 0, it is e raised to minus lambda, lambda raised to 0 by 0 factorial. When x is 1, e raised to minus lambda, lambda raised to 1 by 1 factorial, and so on. Which means that the probabilities we get by putting 0, 1 to etc. in this equation are very similar to the terms of this expansion 1 plus x by 1 factorial plus x square by 2 factorial plus etc. into e raised to minus lambda. Therefore, this total probability of this e raised to minus lambda, lambda raised to x by x factorial for the value 0, 1 to etc. will be 1. And we can treat that this is the starting point of getting this equation e raised to minus lambda into lambda raised to x by x factorial. Now we use the notation x follows p of lambda, where this p stands for Poisson, to represent this random variable x obeys Poisson distribution. Lambda is called the parameter of Poisson distribution. Now we can also consider this Poisson distribution along the lines of binomial distribution. We found that in binomial distribution, x represents number of successes in n trials. You can see that when the number of trials is very large and probability of success is very small, the number of successes can be approximated using Poisson distribution. That means if n is very large, then the Poisson distribution is associated with the occurrences of rare events. Rare event is the event where probability of occurrence is very negligible. Therefore, an event with a negligible probability is called rare event, and when n tends to infinity and p tends to 0 such that np equals lambda, this n tends to infinity means the situation where number of trials is large, and p tends to 0 is the situation of rare event. Then we consider the product of n and p as the constant lambda. Then number of success distribution can be approximated using Poisson equation. Naturally, number of success is considered to be variable following binomial distribution. But when these two conditions hold, then the number of successes can be approximated using the equation of Poisson distribution, which is given by this e raised to minus lambda, lambda raised to x by x factorial. We can illustrate this with the help of some values of n and p, and also the probabilities computed using both equations, that is equation of binomial distribution and equation of Poisson distribution. So let us look upon this table. This n is the number of trials. We consider the values of n like 10, 50, 100, etc. and p as 0.1, 0.02, etc. And lambda is product of n and p. You see, everywhere we can see that this 10 or into 0.1, 1 or np is equal to 1. Everywhere the value of lambda will be 1. So the next two columns show the probabilities of the point x equal to 0 as a test case with respect using the binomial equation and also the Poisson equation. So probability of x equal to 0 is 0.3487 using this equation nc0, 0.1 raised to 0 and 0.9 raised to 10, that is 0.9 raised to 10. So you can see its value is 0.3487. The same zero value probability is computed using the equation of Poisson distribution, that is lambda equal to 1. So p of 0 will be e raised to minus lambda, that is e raised to minus lambda, lambda raised to 0 by 0 factorial. So since lambda is 1, it is e raised to minus 1. So e raised to minus 1 is 0.3679. Here we observe some differences between the probabilities of binomial distribution and probability of Poisson distribution at x equal to 0. But we increase n to 50 and decrease p to 0.02 so that again np equals 1. So the probability using the binomial equation at x equal to 0 is 0.3642, and it is obtained by considering 10 50 z 0, 0.02 raised to 0 and 0.98 raised to 50, and this side it is again lambda 1, so it is e raised to minus 1 only, and it is 0.3679. Now we always take 1 for lambda so that np equals lambda. So always in this column the probabilities will be 0.3679 for the point for the value 0. But here it changes according to the n and p. So it is 0.3660 when n is 100 and p is 0.01. You can see that the difference between 0.3660 and 0.3679 is now less when n increases and p decreases, so that np fixed as 1. You can see the probabilities at x equal to 0 becomes closer and closer, that is 0.3670, 0.3679, and when at n equals 2000 and p is equal to 0.0005, the probability is very close to probability of x equal to 0 using Poisson distribution. That is, using binomial distribution it is 0.3678 and 0.3679 using Poisson distribution. But when n50 and not 50, n5000 and p 0.0002, they become they coincide each other, that is 0.3679 and 0.3679. Thereafter, for any value of n and p, so that np equals 1, these probabilities will coincide each other. So here x equal to 0 is taken as only a test value for the variable x. You can see for all values of this variable x, when n is large, p becomes small, very negligible, such that np equals lambda, then the probabilities of the variable x can be approximated using the equation of Poisson distribution. That is, n tends to infinity, p tends to 0, such that np equals lambda, then x can be considered as Poisson distributed random variable. So in this result, we have a theoretical proof of this property. But before that, we again consider the same property in terms of the graph drawn with Poisson probabilities and binomial probabilities. In this graph, we consider X has binomial distribution with number of trials 10 and probability of success 0.7. We note that NP, that is 10 into 0.7, is 7. So this is the graph drawn in for the binomial 10 0.7 versus Poisson 7. Here these blue squares represent the probabilities generated through the equation of Poisson distribution, while the red cross represent the probabilities generated through binomial distribution. And we find certain differences among the positions of these binomial probabilities and also Poisson probabilities. So that is when n is 10 and p 0.7. The next graph we take n is 20 and p 0.35, so that np is again 7. So the values of the probabilities using binomial distribution and Poisson distribution become closer each other. That means when n tends to infinity, p tends to 0, then probabilities of binomial distributions become very close to the probabilities of Poisson distribution. We in the next graph take n as 80 and p as 0.0875. Again, we can see that the value of lambda, that is n into p, is 7 itself. In this case, we observe that the probabilities using binomial distribution and Poisson distribution coincide each other. They become one and the same. This is the indication of the probabilities can be approximated using Poisson distribution when n is large and p is small, such that np equals lambda. Thank you.